Hi everyone. So lesson 4.4 is going to talk about the last piece um, in terms of homogeneous differential equations. And these are solutions to non-homogeneous equations. So we've looked at linear differential equations that are first order, and then several different types of homogeneous equations. Remember, homogeneous being where this equation here on the left with a second derivative, a first derivative, and the equation y, or some variation of this, okay, maybe we won't have a first derivative, or maybe we, one of those options. And it equals 0 for the homogeneous solution. For non-homogeneous equations, it equals some function b. Okay, that's usually a function of x or a constant. So it could be x, it could be sine of x, it could be x plus sine of x, it could be e to the x. Okay, any one of those functions as a function of x can be sitting here on the right-hand side of the equation. So what you're going to see is that there's actually two parts to solving this. The first part is going to use what we've done for homogeneous equations. The second part is going to look specifically at what this function b is. That is going to determine how you solve this question. Okay? So, like I've said, there's two parts to solutions when the equations are non-homogeneous. And it's made up of the general solution, which you're going to see, I call it YG. Your textbook calls it YC, or the complementary solution, but I like to keep it the same. Remember, we talked about general solutions in our first lesson of this unit, so I like to keep it the same and call it the general solution. But just if you're looking at stuff in the textbook, you'll see it listed like this. The general solution is found using the same methods for homogeneous equations. Remember, where we changed these to be m squared, m, and the y was just a 1, and we equated it to 0. So that's the first half of the solution. The second half is the particular solution. So what you're going to find is your equation y is actually made up of both these parts, the general solution, which I call yg, and the particular solution, which I call y with a subscript p. So you end up finding these two components separately and then adding them together to make your final solution. Okay? To give you some more background on this, I'm going to break this into two parts. I'm going to talk about the general solution, which is YG, and then we're going to talk about the particular solution. And the best way to really look at how to solve these is going to be examples. So we're going to actually cover 3 examples with various types of functions on the right-hand side here. So starting with the general solution, again, I call it y with a subscript g just because we've talked about the general solution in our other lessons. Your textbook calls it yc. So they're the same thing. And I really want to emphasize that if you're trying to also look at some examples in your textbook. And the general solution is found exactly the same way as you saw in our previous lessons. Okay, so 4.2 and 4.3. What you do is instead of having b on the right-hand side, you replace that with 0. Okay, and you solve it the exact same way that you would solve a homogeneous equation. Okay, remember this is only half of the solution. So if you remember that, the d squared, the second derivative becomes m squared, the first derivative becomes m, not m squared, sorry. And the y term you would just substitute 1. So you end up with a quadratic roots expression. Okay, ax squared plus bx plus c equals 0 is our general form. For us, it's whatever our constant is behind the first term, a0 times m squared, plus the constant behind the first derivative, a1 times x, plus a2, which is our constant behind our function y, and that equals 0. So remember, I put an x here, this should say m. So using this, we find the roots either by factoring if there's real and distinct roots or repeated roots, or the quadratic roots formula. And again, you can use the quadratic roots formula for all 3 here. It's totally up to you. Quadratic roots formula, if you remember, is negative b plus or minus the square root of b squared minus 4ac divided by 2a. And that's using, the notation that you'd be familiar with for a quadratic roots function, okay? So once you find these, then remember our original equation was y is equal to the general solution plus the particular solution. So that's going to be this piece of the puzzle in your final answer. And there's no difference in how you solve this compared to our last two lessons. Okay, I stress that a lot. The particular solution really focuses on what exactly is here on the right-hand side of the equation. What is that? Is it x? Is it x squared, 2x squared, okay, sine x, or a combination of these, okay, or a combination adding e to the x, something like that. If your solution to the particular solution needs you to start by doing some estimating, figuring out not only what the function b is, but also what its derivatives are, okay? So the particular solution actually focuses on that particular, or that function that's sitting on the right-hand side, and its associated derivatives, the first derivative and the second derivative. Because remember, this function y here, when you're trying to solve this equation, when you're trying to solve this, remember, the way to solve this equation is the left-hand side has to equal the right-hand side, okay? So your particular solution has to have the function b in it because your function y is sitting here, but it also needs to take into account what the derivatives of that function b are, okay? Because any one of those could be what ends up on the right-hand side as your solution, okay? So the easiest way to look at this is to look at different types of examples of the function b, and we determine what their associated derivatives are, so we can figure out all the pieces that must be in our particular solution, okay? This might seem a little bit confusing, but once I go over some of the different options you have, it should become a little more clear. So what I'm trying to tell you is that you start by looking at whatever the function b is, then you take its first derivative and its second derivative, and you look at all the different combinations of functions there. And for every one of those functions, you have to include it in your particular solution, okay? So what I mean by that is your particular solution, let's look at the first example here, okay? We have the right-hand side function b, our first column, the first derivative of that function b, the second derivative, and then what I'm calling your basic form. This is the form of your particular solution you're going to substitute in, okay, to find your answer. And when you substitute in, you're going to be able to solve for these coefficients, okay? So these coefficients, I have a and b and c, I have d in one instance, they're just constants, okay? It could be 2, could be 1 over 3, it could be 1 over 6, all right? They're just constants that we're going to solve for. Just like when we talked about integration by partial fractions. So looking at each of these examples, if on the right-hand side of your equation you have x squared, you do that, you see x squared, you take the first derivative, it's 2x. Then you look at your second derivative and it's 2. So you have three separate functions here. You have one that's just a constant, which is 2. You have one that's a function of just x, and you have one that's a function of x squared. So you have three different functions here. And so your particular form has to include each one of these, the x squared function, the x function, and the constant. So your general form is a times x squared, because we don't know what a is, plus b times x plus c, or one of each one of these. If it happens, you'll see in the next example, if the same function is there more than once, you only include it once, okay? You don't include it more than once. Our second example is if we have e to the x. Our first derivative is just e to the x, and our second derivative is e to the x. So they're all the same function. So they're all the same. There's no difference in them. So your particular solution only has one piece here, a constant a times e to the x. All right, because there's only one function there. Let's take a look at the next example. What if we combined those? We have x squared plus e to the x. So the derivative of that is just the derivative of each of these individually, which is 2x plus e to the x. The second derivative is 2 plus e to the x. Again, the derivative of e to the x is always e to the x. So looking at the types of functions we have here, we have an x squared. We have a term with just x. We have a constant. And we also have an e to the x term. We have it 3 times, but again, it's the same function, so you only include it once. So we have 4 functions. That means our particular solution must be made up of 4 different functions. A times an x squared term, plus b times x, plus c, which is just a constant, plus d times e to the exponent x. And it doesn't matter what you call these constants, it doesn't matter what order they're in, because you're going to solve for them regardless. Okay, you're going to find a number for them. It doesn't matter if you put the x term first or the x squared term first. Okay, the important thing is you take one of each of those functions and you include it in your basic form for your particular solution. Let's look again. I have 2 more examples. Okay, and then I'm going to explain what you do to solve them. And the best way to do that is to look at an example. So our next function is x times e to the x plus 1. So the first derivative of this, for x times e to the x, you use the product rule. So the product rule is the derivative of the first term x, which is 1, times the second term. So we're left with just e to the x, plus the derivative of the second term, which is e to the x, times the first term, which is x. So you get x times e to the x. And the derivative of 1 is simply 0. Okay, so it's not included here. If you take the derivative again, your second derivative, the derivative of the first term, e to the x, is just e to the x. And we have x times e to the x again. So the derivative, remember, is the same thing. It's this entire piece in brackets. So we add that on, plus e to the x plus x times e to the x. So here, okay, we have 3 separate terms. We have an e to the x. Okay, and you see we have it, 3 times. We only include it once. We have x times e to the x, right, which is a separate function, x times e to the x. And we have a constant. Okay, so we have 3 different functions here. So our particular solution would be a times e to the x, that first function. Again, it doesn't matter what order you do it. Plus b times x e to the x, that second function. Plus c, which is just our constant, because remember we had a 1 here. So when you're doing your particular solution, I will give you this table as a basic starting point so you can understand them. But just know that every time you're looking at them, you just count the different functions. Okay? Our last example has sine. So we have x times sine of x. Our first derivative, again using product rule, is the derivative of the first term, x, which is 1, times the second term. So we have just sine of x, plus the derivative of the second term, which is cosine of x, times the first term, x. Doing this again, okay, the derivative of the first term, sine x, is cosine of x. And again, we do product rule, and x times cosine of x. So we start with the derivative of x, which is 1, times the other term, which is just cosine of x, plus the derivative of the second term, which is negative sine x, times the first term, which is x. So if you look here, we have 4 different terms. We have a sine of x term, a cosine of x term. We have x times sine of x, but we have it twice. Again, we only use it once. And we have an x times cosine of x. So we have 4 terms here, meaning we include all 4 of them in our basic form with constants. So we have a times sine of x plus b times cosine of x plus c times x sine of x plus d times x cosine of x. Okay? I really want to nail home the importance of just counting the different functions. Okay? It's the simplest way to develop this basic form to which you'll solve your particular solution. So now you're wondering, okay, well, I have this basic form. What do I do with it? Well, you go back to this equation that we started with, and you take the particular solution, the derivative of that particular solution, and the second derivative of that particular solution, and you substitute them in here for the second derivative, the first derivative, and the function y, and you solve for these coefficients depending on how many you have, a, b, c, or d. And we're going to do it the exact same way that we did it for partial fractions, where we equated, okay, if we have an x squared term, we have 2x squared on the left-hand side and ax squared on the right-hand side. We equate those coefficients, so we know that 2 must be equal to a. We're going to use that same method that we talked about in partial fractions to solve these functions, okay? And I think the easiest way to show you this is to show you examples. So I'm going to do, like I said earlier, 3 examples where I do these solutions. And then obviously more during tutorial and class sessions, okay? So if you have any other ones, we can always go through them as well. Okay, so let's jump right into an example so you can see exactly how to find the general and particular solutions. So solve d squared y by dx squared plus dy by dx minus 2y is equal to x. So remember what I said, that this function is now made up of 2 parts, the general solution plus the particular solution. So the general solution is what we start with, and it's found the exact same way. By substituting in, okay, m squared for d squared y by dx squared, m for dy by dx, and just 1 for the 2y, and setting this equation to 0, okay, because we're just trying to find the first piece. So if we do that, we're left with m squared plus m minus 2 is equal to 0. So this will actually factor because positive 2 and negative 1 multiply to negative 2 and add to positive 1. Okay, so if you factor this, you get m plus 2 times m minus 1 is equal to 0. So m plus 2 is equal to 0, or m minus 1 is equal to 0. Remember, because one of those 2 sets of brackets has to be equal to 0. So m is either negative 2 or 1. So our general solution is then, remember, because these are real roots that are distinct, it's c1 times e to the m1x plus c2 e to the m2x. Substituting those in, our general solution becomes c1 e to the negative 2x plus c2 e to the x, okay, because m is 1. So our general solution is found the exact same way. Our particular solution, remember, we look at our function b and then we create our basic form from that. So I'm going to start, okay, I'm going to do it up here in the right corner. So our function b is x. Our first derivative, I'll write it as b prime. I think it's easier than writing first derivative in letters. So our derivative is 1. Our second derivative, I'll call it b double prime, is simply 0, okay, because there is no derivative, or you could just put a dash. So our basic form we have two different functions here. We have a function x and we have a constant. So our basic form must be a times x, right, our function of x, plus a constant, which is b. Okay, it's as simple as that, looking at those, and that's how you develop these expressions. Okay, so what that means is our basic form, which is our basic form for our particular solution, is ax plus b. So now we have the particular form, we need to find the first and second derivative of it so we can substitute it into this equation. So we have that our particular solution is ax plus b. Our derivative of it, I'll call it yp prime, is simply a, because the derivative of ax is a, the derivative of b is 0. And our second derivative, yp double prime, is simply 0, right? Because the derivative of a constant is 0. So now we take those and we substitute them into this equation. So what we have is, we'll start by writing the equation, d squared y by dx squared plus dy by dx minus 2y is equal to 0, or not 0, sorry, it's equal to b, which is x. Substituting these in, our second derivative is 0, plus our first derivative, which is a, minus 2 times our function y, which is ax plus b, and that has to equal x. Remember, this equation has to be equivalent. That's why we're trying to find what these constants are. So if I multiply this out, I get 0 plus a minus 2a times x minus 2b must be equal to x. So now, remember all the way back to Unit 2 when we talked about partial fractions. We can solve for these by creating equations equating the coefficients. Okay, so we have an x on the right-hand side and a negative 2a on the left-hand side, so those must be equal. Negative 2a must be equal to the coefficient behind the x term, which is simply 1. And then we have two constants, a minus 2b, and those have to equal 0, right? Because there's no constant term on this right-hand side. So starting with our first expression, if we solve this, we get that a is equal to negative 1 over 2, okay, dividing both sides by negative 2. For the second expression, we get that a must equal 2b, moving the 2b to the other side. So negative 1/2 must equal 2 times b. Dividing both sides by 2, we get that b must be equal to negative 1/4. So what that means is that our particular solution is ax plus b, and it must be negative 1/2 times x minus 1 over 4, substituting those values in. So now that we have our general and our particular solution, our final answer is just adding those two together, right? So we have that y is equal to our general solution plus our particular solution. So y is equal to c1 e to the negative 2x plus c2 e to the x minus 1/2 x minus 1 over 4. Okay? And as you do more versions of the particular solution, you're going to pick up this basic form very quickly. Okay? Another thing to note is, again, it doesn't matter what order or what you call the constants, okay? Like a and b up here, or what order you have c1 and c2 in. If you look at my solution down here, I have c1 and c2 opposite, right? I have c1 e to the x instead of, in my solution or in my version here, I have c2. It doesn't matter, right? Because c1 and c2 are just constants, they're just numbers, okay? We don't know what they are, but they're just numbers. It doesn't matter what order they're in, okay? Okay, so let's look at a second example. D squared y by dx squared plus 4y is equal to e to the 3x. So we start, remember, our function y is equal to our general solution plus our particular solution. So we start by finding our general solution. and we have that we don't have an m term here, you'll see, which isn't a big deal. It actually simplifies things a lot. So we have m squared for the first term plus 4, okay, because we do not have a first derivative in this, so we don't have a term, just m. And remember, we're finding the homogeneous solution, so that's equal to 0. So if I solve for this, I move the 4 to the other side, I get that m squared is equal to negative 4. So m is equal to plus or minus the root of negative 4. Remember, it's under the root sign, so it's a complex number. So that's equal to plus or minus I times the root of 4, or m is equal to plus or minus 2i. Okay? So we have a complex number here, and remember back to when we had complex numbers, our basic form looked a little bit different. We had y was equal to e times alpha of x multiplied by c1 cosine beta times x, sorry, that's a bad x, plus c2 times the sine of beta times x. And remember, alpha was the term before, I'll do it in a different color, the plus or minus sign. So we don't have an alpha here. The alpha here is actually 0. The beta is the term on the other side with where the complex number is. In this case, our beta is 2. So our alpha is 0 and our beta is 2. So substituting those in, we get that y, again, I forgot to write general, so I'll put the subscript of g here. So our general solution is e to the exponent 0 times x. Remember, anything to the exponent 0 is just 1, so that's going to cancel out, times c1 cosine of 2x plus c2 sine of 2x. Okay, remember, since this just cancels, our general solution is simply c1 cosine of 2x plus c2 sine of 2x. Okay, so again, as simple as that, you follow the exact same methods from our last 2 lessons, and you have the first half of your solution to this problem. The second half, or the particular solution, looks at what the function b is. So b, again, I like to write it as a table just so I can familiarize myself with what the terms are. So b is e to the 3x. The first derivative, again, I'll call it b prime, is e to the 3x times the derivative of the exponent, which is simply 3. The second derivative is the first derivative, which is 3 e to the 3x, times the derivative, again, of the exponent, which is 3. So that comes out to 9 e to the 3x. But what you notice here is it doesn't matter that they have a number behind them. They're all the same function being e to the 3x. Okay? So your basic form for this function, okay, is actually just, okay, writing our basic form, is just a times e to the 3x, okay, whatever our function is here, okay? So that's our basic form. In other words, that's the value for a particular solution here that we're using, okay? So that means that we have our particular solution is a times e to the 3x. Its first derivative is equal to a times e to the 3x, again, that doesn't change, times the derivative of the exponent, which is 3, which comes out to 3 times a e to the 3x. Our second derivative is equal to 3 times a e to the 3x, again, multiplied by the derivative of the exponent, which is just 3. So our second derivative is 9 times a e to the 3x. Okay? So remember, we go back to here and we substitute it back into this original equation. So we have d squared y by dx squared plus 4y is equal to e to the 3x. Substituting these in, our second derivative is 9 times a e to the 3x. And we have plus 4 times our original function y, which is a e to the 3x. And that has to equal e to the 3x on the right-hand side. So you can simply add these up. 9a plus 4a gives us 13a e to the 3x has to equal e to the 3x. Okay? Remember, we have e to the 3x on both sides, so we can just equate their coefficients. That means that 13 times a must be equal to the coefficient on the right-hand side, which is just 1. Or in other words, a is equal to 1 divided by 13. Substituting that back in, that means our particular solution, which is a times e to the 3x, is simply 1 over 13 e to the 3x. Okay? So now we have both pieces, and our final answer, y is equal to our general solution plus our particular solution. So y is equal to c1 cosine of 2x. Sorry, I need more space. Let me just erase this. So y is equal to c1 cosine of 2x plus c2 sine of 2x plus 1 over 13 e to the 3x. Okay, so we followed the same method, right? Everything is done in steps. The major piece you have to think about and consider is going to be what this basic form needs to be. Okay, and that's why I like using this table format. So it lays everything out for you to pick out all of the individual functions. Okay. Okay, so our third and final example for this lesson, I've made this one considerably longer. There's a lot more on the right-hand side. As you'll see, there's 2 expressions. But I want to show you that regardless of how complicated the right-hand side of the equation is, the method to solve it is exactly the same. Okay, it doesn't change just because the right-hand side gets more complicated. You know, the algebra you have to do becomes longer, but solving it doesn't become really any different. So we have to solve d squared y by dx squared minus 4y is equal to x times e to the x plus cosine of 2x. Okay, so we've got a lot of different options on the right-hand side. And now I've added a trigonometric function. Okay, so we'll start by finding the general solution. Okay, so our formula, remember, y is equal to our general solution plus our particular solution. So in this case, we have d squared y by dx squared minus 4y. That becomes m squared minus 4. And again, it's equal to 0 for the homogeneous solution. So m squared is equal to 4, moving that 4 to the other side. So m is equal to either plus or minus 2. So they're distinct roots. m1 is equal to positive 2, and m2 is equal to negative 2. Okay, so they are distinct roots. So our general solution, y, is equal to c1 times e to the first root, negative 2x, plus c2 e to the positive 2x. Okay, again, it doesn't change. I didn't write g here, but I should, just so you know. Again, it doesn't change. You still find the roots that way. The second half is where it changes. Okay, so we have x times e to the x plus cosine of 2x. So I start the same. b is x times e to the x plus cosine of 2x. Our first derivative, okay, the derivative of the first term using the product rule is the derivative of the first term x, which is 1 times e to the x, so just e to the x, plus the derivative of the second term, which is e to the x times the first term. So we're left with x times e to the x. And then we have the derivative of the second term, cosine of 2x. Remember, the derivative of cosine is negative sign. So we have minus sine of 2x times the derivative of the function inside the sine, which is 2. Okay, so simplifying this, we get e to the x plus x times e to the x minus 2 sine of 2x. Okay, just moving the 2 out front. Our second derivative, okay, following the same example, derivative of e to the x is e to the x. The derivative of x times e to the x, we've already solved it. Remember, it's this piece in blue brackets. So we have plus e to the x plus x times e to the x. And the derivative of sine x is cosine of x. So we still have minus 2 times cosine of 2x, again multiplied by the derivative of what's inside the cosine function, which is 2. So that would simplify to be minus 4. I'll just erase it so I can write it in here. Minus 4 times cosine of 2x. Okay? So just like we did, we now count all of the different functions that we have here. So we have an e to the x and an x times e to the x. And we have those multiple times, but remember, it doesn't matter. Okay, we only count it once. So for this many functions, what I find the easiest thing to do is I'll take, let's say, even a different color, and I'll cross out all the ones that I've already counted. So I've already counted these e to the x and the x times e to the x. So that's 2 functions. Then next, I have sine of 2x, okay, with different constants behind it, but again, it doesn't matter, okay? So we have a sine of 2x term, and we have a cosine of 2x, okay? So the cosine of 2x we can highlight here. We can cross out the other one. Again, it doesn't matter if we have constants behind them. So what we're left with here is that our particular solution must be equal to a times, you can pick any one of them. I'm going to put the sine and cosine first. So a times sine of 2x, it's our first function, plus b times cosine of 2x, okay, plus our third function, c times e to the x, and our fourth function, d times x e to the x, okay? So that's taking into account all of the green ones that I've circled there below, okay? So again, the method's the same to find the particular solution. It's just you're going to notice the derivatives and the substitutions all just get lengthier, okay? So now we need to find the first and second derivative, so we can substitute. In this case, we're just substituting the second derivative in, but you have to find the first derivative anyways in order to find the second derivative. So the first derivative, we'll call it yp prime, is equal to the derivative of the first term, which is a times cosine of 2x times the derivative of 2x, which is 2. Derivative of cosine for the second term is negative sine, so we have minus b times sine of 2x times, again, 2 for the derivative of 2x. The third term remains as c times e to the x, okay, because derivative of e to the x is just e to the x. And the fourth term becomes d times, remember, the derivative of x times e to the x, which we solved up above here, is e to the x plus x e to the x. Okay, so I won't do that one again. Just remember, every time you see an x times e to the x, you know that once you solve that derivative using the product rule once, you can use it in subsequent derivatives because you're always going to find, a first and a second derivative here. So simplifying this, just multiplying the d through, we get that yp prime is equal to, I'll also simplify the coefficients, 2a cosine of 2x minus 2b sine of 2x plus c times e to the x plus d times e to the x plus d times x e to the x. Okay, so again, you're seeing that it gets a lot longer, but these derivatives are just the same derivatives you've been doing all course. So our second derivative, yp double prime, is equal to, the derivative of cosine is negative sine, so we get negative 2a sine of 2x times 2 for the derivative of 2x inside the sine, minus 2b, derivative of sine is cosine of 2x, again multiplied by 2 for the derivative of 2x. The next two terms just have e to the x, so they stay the same, so plus c times e to the x plus d times e to the x. And our last term, again, remember the derivative of x times e to the x, we've already solved that, is plus d times the derivative of x times e to the x, which is e to the x plus x times e to the x once again. So simplifying this, we get that yp double prime is equal to negative 4a sine of 2x minus 4b cosine of 2x. And I'm actually going to combine all of the coefficients behind just the e to the x terms. So we get for this one, we have a c, okay, and again I can cross them out once I'm done here. And we have a d times e to the x and a d times e to the x. So we get plus 2 times d e to the x, plus our last term, which is d times x e to the x. Okay, so again, a lot of terms here, but we'll do our best to simplify them. So now we have all of our functions we need to substitute it into this equation up top. So you're going to see it's going to take me the whole kind of length of the slide here. Normally I try and do them in columns. But to make it easier, I'll draw a line here as straight as I can. I'm left-handed when I write, so that's why I don't draw the straightest lines when I'm writing them on here. So we have our second derivative. Okay, remember I'm substituting into this function up here. So we have our second derivative, which I substitute in, negative 4a sine of 2x minus 4b cosine of 2x plus c plus 2d e to the x plus d times x e to the x. That's our first term. And that's minus 4 times our original function y, which is a sine of 2x plus b cosine of 2x plus c e to the x plus d times x e to the x. Okay, and that all equals what's on our right hand side, which is x e to the x plus cosine of 2x. Okay, so I told you it would take this whole length. We're going to now start to combine all these together into, with one coefficient. And then we'll look at doing the equating them together. So we have, I'll try and do them in separate colors. Negative 4a sine of 2x minus 4a sine of 2x. Again, I'm going to distribute this 4 into all four of these terms. So that leaves us, I guess doing this in green, with negative 8a sine of 2x, okay, for the first term. I'll switch to blue. We have negative 4b cosine of 2x, again, minus 4b cosine of 2x, distributing in that negative 4, which gives us minus 8 times b cosine of 2x. Switching to, let's do purple. For the e to the x terms, we have a c plus 2d here, and we have a negative 4 times c here. So we're left with c minus 4c. Okay, again, c times e to the x distributing in this negative 4, and a c plus 2d. So c minus 4c, we'll do plus negative 3c plus 2d times e to the x. Now our last one, let's do it in this orange color. We have a d times x e to the x and a negative 4d x e to the 2x, or e to the x, sorry, right? Because distributing in the negative 4. So what we're left with is minus 3d x e to the x. And that's all equal to, keeping red for the other side, x times e to the x. Actually, I'll do them in the same color so you can kind of see the direct comparison. X times e to the x for the first term, and a cosine of x term, which is plus cosine of 2x. Okay? So now we can do the same thing where we equate the coefficients together. Okay? So what we have is we only have sine of 2x on the left-hand side, not the right-hand side. So what that means is that this negative 8a must equal 0. So what that means is a is 0, and in other words, not in our final solution. So a sine of 2x term is not in the final solution. For cosine, we have it on both sides. We have negative 8b on the left-hand side must be equal to 1. So that means that b must be equal to negative 1 over 8. Okay. I'll do e to the x in a second because you'll see it has two terms, so we'll do it last. We have an x times e to the x on both sides. So negative 3d must be equal to the coefficient on the right-hand side, which is 1. So d is equal to negative 1 over 3. In our last term, we have negative 3c plus 2d for our e to the x term, and we don't have an e to the x on the right-hand side, so that's equal to 0. Solving for this, okay, moving the 3c to the other side, we get that 2d must be equal to 3c. And we know that d is negative 1 over 3, so I'll erase that and just do 2 times d, which is negative 1 over 3, is equal to 3c. Dividing both sides by 3, we get that c must be equal to negative 2 divided by 9. So we finally get to the answer, and we have our general solution plus our particular solution. So we get that y is equal to our general plus our particular solution, which is equal to c1 e to the negative 2x plus c2 e to the 2x plus our particular solution. In our first term, if you want to look back up here, you can follow along. We have our first term, a times sine of 2x. Remember, a is 0, so that term, it goes away. Cross it out. We have b times cosine of 2x. b was negative 1 over 8, so we have minus 1 over 8 cosine of 2x. We have c times e to the x. c is negative 2 over 9, so we have minus 2 over 9 e to the x. And our final term, d times x e to the x. d is negative 1 over 3, so we have minus 1 over 3 times, it's a bad one, x e to the x. Okay, so that is our final solution. And you see here, there's a lot of steps. This is a very long solution, but this is one of the benefits to really showing your work when you're doing your answers on a test, because it's very easy to confuse a sign, right? A negative, get a negative confused, doing simple addition wrong of each of these terms. You see, it's simpler to follow along with them, when they're color-coded. You're not going to be able to obviously color code them. I mean, you're welcome to in a test if you want to get colored pens, but a little harder to kind of do it that way. But just following kind of the math to this, if you make a simple mistake of a sign or something like that, you saw that I usually don't take off many marks, you know, half a mark or a mark if the rest of your solution is correct. Okay, so just keep that in mind when you're looking at these solutions. So that was all I had for this lesson for non-homogeneous equations. It probably seemed like a pretty short lesson until we got to the last example because it took a long time to do. I don't have very many practice exercises here. If you are looking for additional ones to do, let me know. I have examples from other calculus textbooks on this subject that I can give you if you're looking to do more examples. You're welcome, you know, I always caution you to try doing examples that I don't ask you to do specifically here, but I mean, you're welcome to try them and ask me questions if you like, but these are the ones that I specifically recommend. Okay, so thanks everybody.